Hello everyone, we are from group 4 and today we are going to presenting about the learning issue for case study 3A. Our group member consists of Kritika, Monabir and Haikal. Next slide. This is the learning issues that we are going to discuss, which is the transfer function of sensor, closed loop and transmitter. And also we are going to discuss about the Matlab Simulink. We are going to discuss about the transfer function of the sensor. Transfer function describes the input, which is the stimulus, and output, which is the response of a sensor system. Transfer function can be represented as table of values, graph, formula, or a solution of equation. As you can see the graph below, that is one of the example of the transfer function of sensor, which is you can see the pressure sensor transfer function and the carbon dioxide sensor transfer function. Okay, so to be able to get the graph, we have to know the equation first. So this is the equation that I use to get the graph. So first one is the linear. As we all know, the equation is y mx plus c, right? So in this case, they are using s equal to a plus bs, where b is the slope, which is equal to the sensitivity, s is the input, a is the y-intercept, and the big S is the output. And below you can see the graph obtained. And this next is the log function, which is S equal to A plus B log S, which the small s is equal to E big S minus A over B. And you can see the graph below also. Next. Okay, the third one is the power function. And the equation is S equal to AS in the power of K. And the small s, as you can see, the equation. And then we have the polynomial function, and as you all can see, that is the equation, and below is the graph for the polynomial function.
So next we have the transfer function of transmitter. Over here we can see that the block diagram shows a measured quantity to the sensing element, to the transmitter, and then to the transmitted signal, which will go to the controller. The process variable is PVS, and the transmitter output is CS. As we know, transfer function will be output over input. Hence, we get a transfer function of KT, which is transmitter gain, over tau T S plus 1. Tau T is the transmitter time constant.
A control valve is a valve used to control fluid flow by varying the size of the flow passages as directed by a signal from a controller. This enables the direct control of flow rate and the control of the process quantities such as pressure, temperature, and liquid level. As you can see, it gains like steady state change output divided by the change in input. The output is slow and the input is controller output from the signal, and the kV is equal to the F by the M, and we have to use chain rule to get the kV. Sign depends on whether valve fails closed or open. If the sign is plus, that means the valve is failed to close, and if the sign is minus, then it means the valve is failed to open. And the dependence of CV on valve position depends on valve characteristics. Next. This is the basic equation for linear characteristics and equal percentage characteristics. This is the constant valve pressure drop, that is dF by this dCV equal to root over of del PV by GF. And after the pressure drop, we can get the linear characteristics and equal percentage characteristics equation like that. And then after this is the variable pressure drop across the valve. If we differentiate F, we can get that pressure drop equations. After variable pressure drop, the linear characteristics and equal percentage characteristics equation should be like this.
A closed loop control system, also known as a feedback control system, is a control system which uses the concept of an open loop system as its forward path, but has one or more feedback loops or paths between its output and its input. So this is the block diagram of closed loop control system. Based on this block diagram, we can come up with transfer functions relating to its output to its input for each of its four components. So we have to do transfer function for each block diagram for controller, final control element, and for the process, and then the measuring device. So these are the transfer function relating its output to its inputs. These are the equations for process, measuring device, comparator, control action, and final element, where GP, GD, GM, GC, and GF are the transfer function between the corresponding inputs and outputs. The series of blocks between the comparator and the control output is considered as the forward path, which is the GC, GF, and GP, while the block GM is on the feedback path between the control output and the comparator. Next slide, Kritika. So this is the algebraic manipulation of the previous equation. So MS is equals to GF CS. So we by expanding the CS, we will get this one. So by further expansion of epsilon, we will get this one. And then by expanding the Y, we will get this one. So finally, we will get this equation. So after rearrangement, we will get this equation. The first term shows the effect on the output of a change in the set point. For the second term, it shows the effect of the output of a change in the load. So to simplify the equation, let G equals to GC GF times GP. So this one will become G, and this one will become G also. So this one is for the set point, and this one is for load. Next slide, Deepika. So we have two types of control problems, which is servo problem and regulator problem. For servo problem, we will the disturbance does not change, where disturbance is equals to 0. So the equation will become like this. And then for regulator problem, the set point remains the same, where the YSP is equals to 0, and the equation will become like this. We will be considering only the disturbance. Next slide, Deepika. So this is one of the example for closed loop system transfer function. So for this question, the temperature is the control output, while the inlet temperature is the load, and the steam temperature is the manipulated variable. So this is the process flow diagram, and then this is the block diagram. So the equation will become like this. Equation 14.14. And then the parameters tau, A, and K have been defined in the example 5.1 and 9.1, which is tau equals to V over F, A equals to 1 over tau plus K, and finally K equals to UAT over V rho Cp. So for the temperature sensor, we assume that the response of the thermocouple is very fast and its dynamic can be neglected. So the transfer function will be like this. And then for controller, we are letting the TSP set point temperature, and then we will get this equation for the deviation. And then for proportional controller, we will get this equation. For control valve, by assuming it as first order dynamic, we will get this equation according to the block diagram. So we will get the closed loop response as this equation, where GSP is equals to G over 1 plus GM, and G load is equals to GD over 1 plus GM, where it is expressed in this way, where we have substituted the G and GM, and then this is the G load. So these are the closed loop transfer functions of the set point and load. Next slide, Deepika.
So lastly, I will be talking about the last learning issue, which is Matlab Simulink. Simulink is a Matlab-based graphical programming environment which is used for modeling, simulating, and analyzing multi-domain dynamical systems. Its primary interface is a graphical block diagramming tool and a customizable set of block libraries. This enables the rapid creation of block diagrams based on transfer functions, followed by simulation for a given input signal. It offers tight integration with the rest of the Matlab environment and can either drive Matlab or be scripted from it. Simulink is widely used in automatic control and digital signal processing for multi-domain simulation and model-based design. Over here, we have an example of the block diagram on the Simulink interface. That's all from us. Thank you.